Yeah, so I was actually looking down for a second there, but I mean, how many people are actively using Node.js, just out of curiosity? Okay, so some of you, and so it's becoming an increasingly popular runtime in especially the HTML5, CSS, JavaScript type space for a couple of reasons. We're of course the company that it sort of came from. The core team works at the company, so I wanted to actually explain a bit around, where it came from, why it exists, where's it going in the future, as a base runtime, and that's sort of the bit around Node.js within context. Now, at least Node, as far as something that came out of Joyent, we're an 8-year-old company. Most of the engineering here is in the U.S. We actually have at least, upwards of, nearly sort of 100 megawatts of data centers deployed as far as a footprint, and largely owned by, employees and, Intel and basically carriers and MSOs. And there's a couple things that we at least do on my team around base activities, and that is, we do an open source operating system, an open source runtime, and then we basically package all up together and we deliver it as a box or we deliver it on premise. That's effectively what the business does. It's no different than a typical operating system, typical runtime, putting it all together into a basic box. Now, if we look at our industry just in general, and we look at it in a very sort of basic economic sense, there's really not a lot to it. Meaning that we have one basic economic good in our industry, which is just the bit, and we weigh it in bytes. And that's no different than if it's a soybean or a t-shirt or anything that you sort of go and ship around. It's a good. For us in our industry, we actually call latency is our service delivery time, how long it takes one thing to go from one place to the other. We typically call bits per latency bandwidth, and we always put these things inside a container of some type. In fact, at least on things like the standardization of container ships, it's things like Paul Barron's work on packet switching networks in the 50s that actually inspired that standardization. And in fact, one of the bigger problems that we have when we're sort of looking at, especially large-scale infrastructures, is we actually have no metadata on bits. There's no the equivalent of a barcode. We only have it on packets, which is a container on the network. We have it on memory words. We have it on blocks. We have it on CPU registers. And that's sort of basically it. And computers are also pretty simple things. We really just have data that we do compute on, and we send and receive it over a network. And when we start thinking around then just a basic economic model for delivering these types of things as a service, we have a bit that can live in DRAM. We have a bit that lives on disk. We have bits that live in CPUs. And those effectively become the three readily available economic goods that we have. And those are, of course, called commodities. And then it's the movement of them, the sort of IOs, the bandwidths, and so on like that are readily available economic services. Those are the base utilities, network I/O, memory I/O, disk I/O, and we, of course, have a base service delivery time. Now, somewhat boring in a pure application sense, but this is really all there is inside any computer that you ever touch. A bit lives in one of those three places, and it moves along one of those three paths. And so from a large-scale service provider point of view, it's basically how do I provide all three of those commodities, all three of those utilities, and do sort of a guaranteed service delivery time, and you just do that sort of end-to-end. Now, the bigger problem, if we look at the way that the industry is even structured, is you effectively have networking companies and compute companies and data companies. We might call them switch vendors, server vendors, and storage vendors, but they do have often diametrically opposed view of things. And in fact, on the computer side, on the server side, we're a bit sort of held down very much by the fact that we're used to using them as a very big calculator. Literally a guy sitting there just doing math, turning dials, and having a 5 megabyte size hard drive that, of course, is 5 tons and has to be flown around. And even as we sort of sit there and we see within the industry where we've gone from a room-size calculator to now a calculator that sits in front of you, to a calculator that gets shipped inside your home, to even how we started using the internet in the enterprise. You know, very often we would draw these great pictures in the 90s of, you know, 5 people using an application between the hours of 9 to 5. And nowadays, we write a cloud like this, and we talk about things like, you know, HTML5 based multi-device delivery of an application and so on like that, and we draw this. Now, of course, the problem with a lot of this, or at least what the base abstraction needs to be, is we just need to think about what would it be if we just thought of it as a world of devices with the network as the backplane, right? So just everything's a device, the network's the backplane, and if that's the base sort of strata that we're going to operate in, how would we go and design a system that runs that, right? Not how would we deal with legacy cruft, how do we deal with these types of things, how we look at a world of devices with the network as the backplane. And of course, when you look at device users hitting an application, you know, very often are a lot of users hitting an endpoint, a lot of users sort of crushing in, and that does actually happen to be crushing. And so where you typically see a lot of traditional runtimes, a lot of traditional frameworks, a lot of these traditional things basically begin to start having issues now, is when you say have an enterprise application that 5 people used to use, and now you're actually trying to get it to be used by 1,500 sales guys in the field who expect soft real-time access to it on a mobile device. And so that's a different type of application. And it's really historically because we do use computers to calculate things. We actually use them to do math. In fact, that's even what the name computer comes from. Compute means to determine by math. But the problem being that we also use them to connect things. We also use them to do movement. And of course, connecting, where we join and fasten things together, where we actually go ahead and schedule so as to provide some continuing service, that is not how computers are designed. They're designed to be good computers. They're designed to be good at math. They're not actually designed to be good connectors or movers. And in fact, we can go and look inside a data center and we can break down what's inside of a data center in very, very sort of simple nouns. We actually have computers, connectors, movers, and storers. Those are currently the 4 types of devices you have inside a data center. You have a server that does computing. You have a thing that actually, say, connects those things called a switch. You might have an aggregate switch, and then it connects to a router that moves packets around, and you might occasionally store stuff. And the store stuff being that, well, storing things long term does not require you to have a bunch of compute or memory or those types of things in it, and that's 2/3 of the cost of the box, so why spend a bunch of money? And so we really then just have computers, movers, connectors, and stores when we sort of look at what that base thing is. And again, the question becomes, if we think of the world as just a world of devices with the network as the backplane, and we just have to do math, store stuff, connect things, move things, then how would we go ahead and redesign operating systems and runtimes to do that well? And how do we do that in a way that sort of allows us to migrate from the sort of morass that we're in now? And again, the crushing part of it is, you know, there's some trends that are popping up, right? So one, of course, is not only is everything becoming a web application as the base transport mechanism, but more people are using the web. You know, in 2001, there was, what, 200, 300 million people using the internet, and now there's nearly 1 billion people using just something like Facebook. And so the usage is significantly larger than it was a decade ago. Literally, there's 10 times more people on the internet today than there was a decade ago. If you recall in, say, 2000, 2001, what a phone looked like, it was not an iPhone. We did not have iPads. And now I myself, I mean, I have 3 daughters, and they all have iPads. And the 11-year-old has an iPhone. And they all have these types of things like it. And we have TVs that have 4 chips inside of them. We have Blu-ray players in every room. I mean, the typical sort of crap. And so everything really is fundamentally becoming a web app. And because we actually sit down and we start thinking of it really as a world of devices, network is the backplane, the way that we've been writing applications, whether you realize it or not, is changing. We actually don't write client-server applications from a decade or 2 ago. We actually write sort of soft, real-time, data-synced peer type applications. We actually very often have, say, a server on a phone and a server in the back end, and they're passing messages between one another, and then they're also interacting with, say, a local thing that you might call a client. And so what we're really sort of seeing is we're seeing really the sort of presence of soft, real-time expectations in an application that someone uses. We're actually seeing that the way that you write that is not traditional client-server. And if you look at just the limited ways that one goes and does distributed concurrent systems anyway, message passing is one of the types of methods you use as one. So it's already one in the switching space and some other aspects of it. But we still have these arguments now with servers where you're like, well, you know what we should do is we should InfiniBand a bunch of these up and create an operating system that makes these 5 servers look like one big-ass server. And you have a lot of these types of things around RPC and IPC and shared memory and so on like that, when really what it is this message passing as one for doing these types of systems. And it honestly reflects the way humans interact. You text message, you leave a post-it note, you write little notes. And so it turns out we're writing applications that way. The trend around big data is not big. I mean, myself coming from large-scale scientific compute before I started doing, data centers in this space, that's been big data forever. I mean, what we really have right now is an interest in going from user-generated data to machine data, and we have an interest in real-time decision-making from machine data or behavioral data that machines look at about human activity. That's the big data trend. But it really is a real-time analytics type trend, much more so than the size of the data. We've already had telescopes in existence that could put out an exabyte a day, meaning it would take them 2 weeks to exhaust the enterprise storage market. It's 2008 is where we crossed over to the point where if we lit up every DNA sequencer in the world, we would exhaust the world's supply of hard drives that have ever been made in 4 days. And so we have big data in that sort of world that comes from nature, but it's really real-time access. And because we have so many people typically now accessing these applications with mobile devices, and what we actually see is we see that applications are often becoming connection limited, right? And so handling a lot of connections, doing a lot of sort of I/O. And of course, sort of put this within sort of context again, which is where, we started working on Node.js was to actually start working of a data center as a device. Meaning how do I physically and logically design a data center independent of knowing what I'm going to run in it, and actually do this from a very sort of traditional supercomputer type approach, where you can actually take a very sort of traditional coupled synchronous shared memory great at math type compute-bound supercomputer, and in fact most of the world's problems are I/O bound, and so you actually need backends that do that well. They're decoupled, asynchronous, event-driven, non-shared memory where message passing is basically the sort of predominant way. And in fact, if you decided that you were going to design such a thing, it would look more like the back end of a SAN that, say, natively runs compute on it. And so Node became very much the runtime that we were using, as I'll show you in a minute, for creating that sort of large machine-to-machine system across many, many, many sort of data centers. And then, of course, as it started showing up on a lot of devices a few years ago, the sort of end-to-end story got to be pretty well. Now, a lot of this, of course, is doing things well. I want you to run my app well. I want you to keep my data well. When I click a button, I want it to be fast. I want it to do things, like that. And so from a base technology view, again, run applications well, data centers a box, runtimes on devices, flattens everything down to sort of one dynamic language like JavaScript, typically a compiled language like C, got a good markup language, good presentation language, flatten everything out, and then keep things simple. Really sort of go with one instruction set, one transport mechanism, one messaging system, one type of format. And we really have now seen applications emerge, in this way. And emerge in this way in the sense that people start caring about performance and scalability, the resiliency and reliability of the application, whether you can understand what it's doing in production, is it secure, what's the sort of data integrity like, and is it actually elegant, meaning as simple as possible to sort of access it, interact with it, integrate with it, interoperate with it, versus a typical sort of just agility, flexibility, backward compatibility, don't want to upset the boss type way to write an application. And so within that context then, when we start sort of thinking of Node.js, Node.js for a design point of view was we basically needed a framework to just quickly write servers in a dynamic language. So servers that talk a specific protocol, they function as API endpoints, proxies with the policy, load balancers, data ingress, telemetry systems like that. So no different than just a very traditional service-oriented type architecture where you can very quickly write services. But you actually needed to write services that were basically going to be lossless in terms of I/O and were connection intensive, but they were not meant to do math well. And in fact, from a design point of view, one process, one core, less than 1 gig of RAM, is actually QA'd to push line rate 10 gig and do 1 million connected endpoints, where about 25% of them are pushing traffic. Which to put within context is about 20 to 500 times more than what a typical runtime, whether it be Java or Ruby, can typically handle in a single process. And even when you sort of take the memory footprint into account, it becomes more pronounced. And so it's even very normal for us to write 128 megabyte size node processes that will actually push between 1 and 10 gigabits per second of traffic and have 200,000 connected endpoints on it. 128 megs. And so sitting down and thinking about, how one sort of writes applications like that, which then made it very amenable for it to be on device too. And so we have things like it's showing up on the smart thermostats from, Emerson Power, showing up on, now Windows mobile phones, and it was in, WebOS, which of course at least conceptually has, the boot to Gecko from a philosophical point of view sort of overtaking that. But for us, again, it was really around, well, how do we do like a tremendous amount of data? How do we actually do telemetry systems? How do we begin to basically do things like look at a whole lot of servers and connect a specific amount of data, bring it back, graph it in real time. So like not to go too much into say the details of this, but this is a good illustration of what Node was designed to do. In that this is what's called a heat map graph, and so the y-axis is like latency, the x-axis is time. This is about 10 minutes. The far right over there is right now, and this is 10 minutes from now. And this, for example, is looking at about 300 database servers that were part of one of these large games we were running. And there's about 1.8 billion data points in this, in terms of what you see. And every dot that you see is basically like a MySQL query latency, so the actual time it took for a query to happen at a specific point in time. And you can see things like nothing happened here, you have this whole group of latencies there, and then everything gets slower, which is why this is going up, and the whole system basically collapses on itself. This is a very normal sort of graph pattern for like congestive collapse. The equivalent being, walking down the street, having a heart attack, and the ER doctor was able to see, the 10 minutes of your EKG before you died there on the street, right? And so the ability to sort of write a little runtime that goes and collects a bunch of data from a whole lot of devices and brings it back and graphs it up was honestly what Node was designed for. The ability to sort of go and say, what's everything that's running on a server, what's everything that's running in a rack, what's everything that's running in 48 racks, how do we sort of go and basically just write a very large scale telemetry system and do that by even sort of redoing the runtime. Now we open sourced it 2.5 years ago. It's MIT licensed, which is about as liberal as it is. It's not a product of ours. It will never be a product of ours. We don't do a PaaS around it or something like that. We just happen to be the largest production user of it. And in fact, that tends to basically shape its use. Now, besides showing up in every mobile OS in existence and more of those sort of coming out, it's of course a supported runtime like an Azure, right? So .NET, Node.js, and it's actually deployed, the number 2 there after .NET. PaaS like Cloud Foundry from VMware. Node.js is also the second most popular runtime there. And then we see a lot of interesting things, like what was being done, by the guys at eBay, where it was around, how do we actually aggregate a lot of our API endpoints into new endpoints and create a whole sort of, DSL around these types of things, and that was all sort of done in Node.js as well, and that's exactly the perfect type of use point. How do I basically write a service endpoint that aggregates a bunch of other services? And how do I potentially have the devices that I'm interacting with also be those service endpoints? Now, the why JavaScript part became pretty simple. I mean, it's actually called Node.js because there is a Node part that I'll talk about in a second, and then there's the JS part, and they are actually largely independent of one another, even though conceptually more difficult to separate. And that's really because JavaScript happens to be an event-driven language in UIs. UIs are event-driven. And so one way of thinking around, at least philosophically, Node is just the UI way to do things on a server side. Usually servers are not done in an event-driven, non-blocking, meant to be instantly responsive, type way to do things. It has a spec, which not a lot of languages do, not all of them do. And the specification is actually controlled by an international standards body, which is nice. And if you take at least these two base criterias, there's a recent one around Ruby, I believe, but the only thing that typically falls out of these two is things like C, C#, and JavaScript, as far as the base spec. And so what we see is we actually have seen in the marketplace multiple implementations where you're typically competing for performance and embeddability. So Microsoft has multiple JavaScript VMs over time. You have Trace Monkey, Spider Monkey, from Mozilla. You have V8 from Google. You have a lot of these sort of, great examples of a language runtime against a spec open language. That's been a pretty good benefit. Now, the added benefit, of course, is that this now flattens the stack into HTML5, CSS, JavaScript, and say if you still want to write in something like C, it becomes, or C++, it's pretty easy to do. Now, if we look at the Node.js part of the implementations, there's, Node that's under GitHub. The important library part that is Node is a thing called libuv. And then there's some add-ons like the parser, some base instrumentation type things that we do like Node dtrace and Node panic. But the thing that was interesting around the libuv work, was really around, as Ryan's asserting here, as it says, libuv is the world's best cross-platform networking library. What we wanted to do within the Node.js project was take the Node part out and actually make it entirely cross-platform. And so, we worked last year quite closely with Microsoft for the year to sort of sit down and say, well, how can we basically make it so that within the Node part of Node, libuv is a C library, is always basically working on the constraint that if it's not in Windows, it doesn't go in. If it's not in, Unix too, it doesn't go in. But the only basic features that show up from a, I/O abstraction point of view within Node.js is ones that are actually present and can be present across every operating system in existence. Because the goal really is, in fact, to write an application with an exceptionally small footprint that runs on every OS or device in existence, right? To make something very sort of easy. And so the libuv part's actually, if you like to geek out on runtimes, it's a pretty good one to look at. And of course, also sitting there on GitHub as well as a separate thing. And so we see things like the Love It guys, taking libuv and combining it with Lua as a language interpreter, which, in the Node nomenclature, if you will, be node.lua, if you wanted to think of it that way. But being able to take a C library like libuv, combine it with any language interpreter that you can basically combine it, something that's either in C or C++, and give it the features of Node is what libuv is for, and also make it entirely cross-platform as a result of doing that. And so if you really begin to look at that work, libuv coming out, which was part of .6, .8 coming out now, really sort of progressing to 1.0. Node.js is actually done from a, it's done. I mean, there's not too much to do to it. anymore. You know, we're not adding everything under the sun to it. It's meant to actually handle a lot of connections, do a lot of I/O. And so when we start thinking around that sort of basic idea that, well, the runtime's largely done, then it's really just around sort of handling two parts of the implementation. One is making sure that the actual module interface that you can go and write a module for it is exceptionally clean, standard, and won't ever change. And the other one being that it actually is very easy to instrument in production. And so again, if we think about, you know, just some simple examples of that little slide we showed earlier, if you're thinking around things like performance and scalability, the way Node is right now is there's actually nothing left to do with Node to make it better perform or scale better. Most of the times where it's breaking now is more like, you know, the TCP/IP stack of the operating system it's on can't handle as many connections. And so it tends to actually be operating system optimizations to drive the performance and scale part of Node. And yes, it's supposed to be a single process that runs on a single core, and that's the design. It's also not going to be multi-threaded and anything else like that. That lives within a module, if you care about that. And so when you start thinking around the list of doing things well, then most of the efforts that we have remaining within Node.js is really around resiliency and reliability of running that in production, and really around debuggability and understanding it in production. That's actually where you can still do things within Node. And so there's some unique things around Node that we've done to you know, make it good for that. One, it dumps like an operating system. And so literally, it's got a module named Node Panic, where this provides post-mortem debugging of single failures. And so you can sit down and, you know, be running 1,000 of these processes in production. You have one of them that's sitting there at 99% utilization of a CPU, and you can literally go dump a full stack trace out of that, literally dump a core file, and restart that process, pull that core dump out, put it in a kernel debugger, like MDB or GDB that has the module that can read the dump, and go and root cause that error. And so the ability to sort of do these 1 in a billion type bugs that you see and root cause it without disruption means that you can look at a large production environment of this, or you can look at a large deployment across devices, understand what the normal parameters of that application needs to be when it's running, and if it goes outside of that, dump core, restart the process as a regular sort of way of doing things, and then bringing those core dumps in and sort of regularly analyzing them and seeing what comes out. It really sort of allows you, especially in a large production environment, to really go through and find these rare bugs that sometimes, you know the typical things where every 6 months it pops up, you know, and all these things are spinning out of control, and you do the typical, you know, reboot button type way of dealing things. And so it actually has pretty tremendous post-mortem debugging, and we actually do a lot of work around post-mortem debugging in dynamic environments and publish various things in there. If you care about following the engineering lead that works on this aspect of Node, this is his blog. His name's Dave, and it's dtrace.org/blog/dap, and he's got a lot of you know, base you know, sort of things that he does around managing a lot of Node dependencies when you deploy an application, how to actually do very good solid Node V8 post-mortem debugging, you know, as a base capability, you know, where one can really go through and do some very sort of interesting stack traces. And then importantly, one can actually go through and ask, you know, a very simple question that's normally impossible to answer in a lot of other dynamic language environments, and that's like, where's the program spending all of its time? Because especially in something like Node, where it's a language interpreter, and then it's a whole sort of, you know, framework around, you know, handling all the sort of I/O aspects, the ability to sort of, you know, literally trace in and out of that and go across every layer and sit down and say, how long is something spent? One can actually go through and, well, you can't see this here, so I'll show you a picture. One can actually go through and say, graph this into something that's called a flame graph. And so this is a way of visualizing where an application spends all of its time. And so like this is just a very simple single node process that's responsible for making an image. Data, JSON file comes in, creates a PNG file, spits a PNG file out, that's all it does. And so, the way that a flame graph works is the bottom line is the total amount of time. Like it takes a second for the process to do this. And what it proceeds to then do is break out every other possible part of the system and language interpreter and lines of code that it touches and assigns, of course, a time to each of them, and then that's how big the graph is, right? And so, for example, it spends, the equivalent of that amount of time, executing things from, line 4,860, 80 up. And, libpng is up here, libz is up there. And so one thing I think that's particularly interesting around using Node.js in these types of environments, or using it as both an on-device runtime and a data center, back-end runtime, is we put a tremendous amount of effort in one, making it, as I was saying earlier, entirely cross-platform, and then a tremendous amount of effort in just being able to answer two very difficult to answer questions. Where's my application spending its time? And when I see something that's exceptionally rare as a defect, can I go and root cause that, having only seen it once? And so that being the two issues. And it's a bigger problem, especially now if you're running a single process where you've trusted it to handle 1 million connections. Because when the process poo-poos itself, you just cut off 1 million connections. It's not spread across 1,000 application servers, right? And so being able to do that. That's largely Node.